Hey guys, this is Mrs. Harbin, and we are continuing with Unit 7, which is all about radicals and exponents. And today we're going to look at Lesson 3 on how to add and subtract radicals and exponents. And the name of this lesson is Sums and Differences, and we'll be working from Lesson 3 in your book when we do practice problems. Our lesson objective for today is that you, the student, will add and subtract radical and exponential expressions. Remember, radical means there's something under a root sign, and exponential means you have an exponent, like x to the 1/2, or maybe x to the 4/3, or maybe just as simple as x squared. So we'll be adding and subtracting radical and exponential expressions. Let's go ahead and start with a quick warm-up and simplify these expressions. Now, because this is all new to many of you, we're actually going to go through the warm-up just a little bit slower than we normally do. So let's start by taking the cubed root of negative 54 x to the 4th. Now you may see this negative and go, oh, we can't do that. Remember, we can't take roots of negative numbers. We can't take square roots. We can't take even roots of negative numbers, because no number times itself twice gives us a negative number. We can take odd roots of negative numbers, and so this is a perfectly valid expression that we can simplify. One way that we can simplify roots is by listing all the prime factors. So we could do that here for 54. Another way that we can simplify is thinking, do I know any perfect cubes that make up the number 54? And if you're familiar with your perfect cubes, you should know that 27 is a perfect cube, and negative 27 times 2 is equal to 54. If you didn't know that, you would have a prime factorization of 3 times 3 times 3 times 2. So that's another way that you can write that. X to the 4th, I can write as x cubed times x to the 1st, or x times x times x times x. I'm then going to take the cubed root of every single one of my factors. Now negative 27 is a perfect cube. It's a 3. And x cubed is a perfect cube. It's a negative 3. It's an x. The 2 and the x do not have perfect cubes, so they're going to stay under the radical symbol. And when we simplify this, we get negative 3x times the cubed root of 2x. Now remember that the implied operation in algebra is multiplication. So even though there are no parentheses here, this radical symbol acts like a grouping symbol. And the implied operation that's happening here is multiplication. Negative 3x times the cubed root of 2x. All right, take a look at this. 3x squared plus 2x squared. How would we combine that? How would we simplify that? Well, most of you know that we add the exponents, but I've had people ask, well, why doesn't it become x to the 4th? So I'm going to draw a quick little picture to illustrate for you why it's not x to the 4th. Remember that multiplication just means repeated addition, and exponents indicate repeated multiplication. That's a big reason as to why, but for those of you that are still struggling with this, a picture might illustrate this. Multiplication, the multiplication symbol, can be read as, written this way, can be written with parentheses, and it can be also read as groups of. So I have 3 groups of x squared and 2 groups of x squared that I want to add. So let me show you what that looks like. So x squared is just x times x, right? So here's one group of x squared. Here's a second group of x squared. Here's a third group of x squared. And I want to add or combine that with 2 more groups. So there's 2 more groups of x squared. So now I have 3 groups of x squared and 2 groups of x squared. How many groups of x squared do I have altogether? I now have 5 groups of x squared. I didn't change what was being multiplied. It's still only a group of x times x. So my x squared is what's in each group. And this number tells you how many groups. So hopefully a picture like that will help some of you see that here, that we're not changing what's being multiplied. We're just changing how many groups of that we have. So 3 groups of x squared plus 2 groups of x squared equals 5 groups of x squared. All right, how would we simplify this? 5x minus 3 times 2x plus 3. Well, hopefully you said we would distribute, right, to get rid of those parentheses. So we have 5x minus 6x minus 9. And then what would we do? We would combine the 5x and 6x, because negative 6x because those are like terms. And you should be familiar with that terminology. Remember, a like term has to have the same variable being raised to the same power. Both of these is a variable of x being raised to the first power, so we can combine them. This negative 9 does not have a variable, so it's not like the others. And when we combine like terms, we get negative x minus 9. It's going to be really important that you understand these three problems and the basic foundational pieces, the algebraic steps that we took here, because we're going to see some more complicated problems that are going to look similar to this and rely on some of this understanding that we just looked at on this slide. When you hear the term like radicals are just like terms. The like radicals are radicals having the same radicand and index. Remember that what's under the root symbol is the radicand. So if I had 3x, the square root of 3x here, this would be my radicand, and my index is this little number that's right here. And if there's not a number here, then it's implied that's a 2. This is a square root. Remember that I can rewrite a radical as an exponent. So I could rewrite that as 3x to the 1/2. Now, in order to combine that with other things, I would have to have the same variable being raised to the same power. So I could combine 3x to the 1/2 with other terms that look like this. So you're already familiar with like terms, and a radical is just another way to write an exponent. If a like term has a variable being raised to the same exponent, then like radicals, which are just another way of writing exponents, also have to be the same in order to add or subtract them. So they have to have that same radicand and the same index. Only like radicals can be added or subtracted. So just like only x plus x can be added or subtracted, only like radicals can be added or subtracted. Let's try a sample problem here, and we're going to follow these steps. The first thing that we're going to do is simplify each radical that we're trying to add or subtract. Once we've simplified it, we'll combine like radicals by adding or subtracting their rational coefficients. Just like in 3x squared plus 2x squared, the x squared didn't change. The only thing that changed was the 3 plus 2. We added their rational coefficients to get 5x squared. It's going to be very similar when we're adding like radicals. So let's start with root 32 plus 3 times the square root of 8 minus the square root of 18. The first thing that we want to do is simplify each radical. And we're going to do that using either prime factorization or thinking of what factors are perfect squares. So I know, for example, that 32 is the same thing as 16 times 2. I can then take the square root of 16 and the square root of 2 to simplify that expression. And 8 is 4 times 2, and 18 is 9 times 2. So I'm looking for those perfect squares to help me simplify that. Okay, what this becomes is 4, and then the square root of 2, which doesn't simplify, plus 3, and this is times. So when I take the square root of 4 here, this is going to be 3 times the square root of 4, which is 3 times 2, times the square root of 2, which doesn't simplify, minus, and then the square root of 9 times the square root of 2. So that simplifies to 4 square root of 2 plus 6 square root of 2 minus 3 square root of 2. Because I was multiplying 3 times the square root of 4 times the square root of 2, I ended up with 3 times 2. So remember that implied operation here is multiplication. Once all of my terms have like radicals, root 2, root 2, root 2, what I can do is add or subtract using their coefficients. So I'm really only looking at the 4 plus the 6 minus the 3. My root 2 is going to stay the same. So I have 4 groups of root 2 plus 6 groups of root 2. That's 10 groups of root 2. And then I subtract 3 groups of root 2. So 10 minus 3, I have 7 groups of root 2. So again, imagine that these are x's. If I had 4x plus 6x minus 3x, I'm only adding or subtracting the rational coefficients here, 4 plus 6 minus 3. My variable never changes because I'm adding or subtracting the groups. 4 groups of root 2, 6 groups of root 2, minus 3 groups of root 2. It may help you to say groups of, like I just did. That may help some of you kind of visualize what it is you're adding or subtracting. All right, for example 2b, let's go ahead and simplify this. We have the cubed root of x to the 4th minus the cubed root of 8x to the 4th. When the index is 3, when we write the prime factorization, we're looking for sets of 3. So this is x times x times x times x. There's a set of 3 here, so I can write that as x cubed times x. And this is 2 times 2 times 2 times x times x times x times x. So I've got a group of 3 here and a group of 3 here. So 2 cubed and x cubed and x. I'll then take the cube root of each of those factors. And when I do that, I get the cubed root of x cubed x and the cubed root of 2 cubed. Now we'll take the cubed root. So the cubed root of x cubed is x. And the cubed root of x, it can't be simplified, so it stays there. And the cubed root of 2 cubed is 2, so that comes out. The cubed root of x cubed is x, and the cubed root of x stays in there. As you can see, I now have like radicals. So I have just these coefficients that I'm going to combine. My radical will stay the same. So I have x groups of cubed root of x minus 2x groups cubed root of x. So x minus 2x is all I'm worried about. X minus 2x is negative x, so I'm left with negative x cubed root of x as my final answer. All right, here's our next example. Let's simplify this expression. The first thing that we want to do is simplify each radical. So we're going to do that using prime factorization or by looking for perfect squares. So 72, for example, is 36 times 2. That's a perfect square. Don't forget, when we're taking square roots of negative numbers, that we're introducing this square root of negative 1, and as a reminder, the square root of negative 1 is I. So each radical simplified becomes 6 root 2 plus 6i minus 7 root 2 minus 3i. The 2 in blue I can combine because they are like radicals, and the 2 in red I can combine as well. So when we combine our blue terms, 6 groups of root 2 minus 7 groups of root 2, I get negative 1 group of root 2. And my red terms, 6i minus 3i is positive 3i. Now, it does look like I'm going to run out of time before I get through all these examples. So there will be a part 2 for this, and I'll try to stop it at a reasonable spot here. When adding radicals, just as radicals must have the same radicands and indexes to be like terms, exponential terms must have the same bases and exponents if they are to be combined as well. So in part 2 of this video, we're going to take a look at how to add or subtract exponential terms. We just did radicals and looked at like radicals. Part 2, we'll look at exponents. If you have any questions so far, write those down and be sure to ask me next class.